Welcome. This is the second presentation in a series of technical presentations available to support the draft supplemental guidance, Screening and Evaluating Vapor Intrusion. This presentation provides a summary of the draft guidance. My name is Cheryl Prowell. I work for the Department of Toxic Substances Control and am a member of the Cal EPA Vapor Intrusion Workgroup. In response to the COVID-19 crisis, the Cal EPA Workgroup is providing these presentations as modules for public viewing at your leisure during the public comment period for the draft guidance. If you have questions on this presentation, please send them to dwq-vaporingtrusion@waterboards.ca.gov with the subject line of Overview Presentation Question. Here is an outline of this module of the presentation. First, I will describe the conventional conceptual site model for vapor intrusion. Then, the new conceptual model for vapor intrusion caused by sewer air. I will explain the reasons for this guidance update. Then I will hand the presentation over to Dan Gallagher, who will provide detail on the guidance itself. The conventional vapor intrusion conceptual model begins with a release to soil and groundwater. In this figure, contaminated soil is shown in orange, and contamination dissolved in groundwater is shown in gray, near the bottom of the slide. Vapor-forming chemicals can partition from contaminated soil or groundwater, moving into soil vapor. Near the source, vapors migrate via diffusion, moving from areas of high concentration toward lower concentration. Closer to a building, vapors also move via advection, moving with airflow up into buildings. An intact foundation can impede the flow of vapors, but vapors can move through cracks in the foundation or around utilities. Buildings typically allow ventilation or air exchange with outdoor air, causing vapors to dilute. We use the concept of attenuation factors to predict concentrations in indoor air based on concentrations in the subsurface. As I just described, concentrations in indoor air tend to be lower or attenuated because the building foundation acts as a barrier and building ventilation provides dilution with outdoor air. Attenuation is the concentration reduction along the flow path. The attenuation factor is the mathematical expression of this reduction. In this example, the concentration in soil gas is 500 micrograms per meter cubed. In indoor air, the concentration is 10 micrograms per meter cubed. The attenuation factor is defined as the concentration in indoor air divided by the concentration in soil gas, or 10 over 500, which equals 0.02. This represents an attenuation or reduction in concentration of 50 times between soil gas and indoor air. In the last several years, there has been research showing that vapors can also migrate into buildings via sewers or other utilities. Many sewers were designed to gravity drain, and the pipes were never designed to be vapor-tight. If these sewers intersect areas of contamination, contaminated groundwater or highly concentrated soil vapor may enter the sewer, allowing vapors to move quickly through the sewer into buildings. Vapors can move inside the utility pipes, not just through the bedding material surrounding the pipes, and can enter the building if P-traps are allowed to dry out, if there are breaks in the pipe inside or near a building, or if there are faulty gaskets on toilets. Also, as shown in purple, land drain systems designed to prevent water from flooding a basement may also be providing a conduit for contaminated vapors to travel. What are the reasons for this update? The existing guidance is dated. What's out there now is DTSC's 2011 Vapor Intrusion Guidance and the San Francisco Bay Region's 2014 Trichloroethylene Framework. Both of these documents are over 5 years old, and science is rapidly evolving. There is new information about preferential pathways, such as the sewer pathway, that I just discussed. Within the last 5 years, there has also been research on the variability of vapor intrusion, and as shown in this slide from Paul Johnson, there can be spatial variations on the order of 2 to 100 times, and temporal variation of up to 3 orders of magnitude. When we started developing the guidance, both the TTSC and the Water Board recommended attenuation factors based on the Johnson-Ettinger model for deeper soil gas and groundwater. Model-based attenuation factors are shown in blue. In 2015, US EPA published guidance recommending attenuation factors based on an empirical database of attenuation factors observed in buildings nationwide. Empirically based attenuation factors are shown in green. DTSC's sub-slab attenuation factor was based on an early version of this database. The range of attenuation factors creates confusion. With a difference of 25 times between the Water Board and DTSC, there may have been times when the Water Board may have concluded that a building had a low risk for vapor intrusion, when DTSC or US EPA would have concluded that more action was needed. Cal EPA has committed to providing a consistent set of standards, adopting US EPA's recommendation. This slide highlights the key updates. As I mentioned on the last slide, for screening, this guidance recommends the use of US EPA's empirical attenuation factors. These factors are 0.03 for soil gas and 0.001 for groundwater. The guidance provides supplemental guidance for sampling. The core of the guidance is a four-step process to determine if a building is at risk from vapor intrusion. There are also attachments to deal with special situations, including other building types, petroleum-specific considerations, and sewers as preferential pathways. We know that there are concerns that US EPA's nationwide database may not be appropriate for California because our climate and typical building construction may lead to less vapor intrusion. To address this, we have updated GeoTracker, the Water Board's online records database, to better collect vapor intrusion data. This allows us to bring together data gathered on a site-by-site basis to evaluate vapor intrusion, to create a unified California-specific database. The database can be used to better understand the factors influencing vapor intrusion and potentially develop California-specific attenuation factors. The guidance adopts US EPA's 2015 attenuation factors for screening. What was the basis for this decision? It aligns Cal EPA with the federal approach. Typically, states should not be less conservative than their federal counterparts. It follows the example of other states. Most guidance published since US EPA's attenuation factors were proposed have followed their lead. We are not setting precedent with this decision. Comparisons of the Johnson and Ettinger model to the empirical database show that the model cannot predict the range of attenuation factors observed by US EPA, and the model is biased low. Using the model may underpredict risk and lead to decisions that are not adequately protective. Potential future changes in the building may result in changes to the attenuation factor over time. So modeling for planned building use, or even sampling just after occupancy, may not be representative of the range of attenuation factors that a building could experience over the life of the structure. Finally, models do not address preferential pathways. This slide depicts the empirical database published by US EPA in 2012 that is the basis for the recommended attenuation factors. Indoor air concentrations are shown on the x-axis, and subslab concentrations on the y-axis. The diagonal lines across the plot depict various attenuation factors, with a 1-to-1 ratio shown by the red line, a 1/10 attenuation factor shown by the solid blue line to the right, and an additional order of magnitude reduction for each blue line. The database was developed based on 41 sites in 15 states, 6 of which are in California. It includes 431 pairs of subslab and indoor air data, where the subslab concentration was more than 50 times background concentrations. The majority of the buildings in the database are residential. This green line represents the recommended attenuation factor. It is the 95th percentile of the database, meaning that 95% of the dots fall below the line. An attenuation factor of 0.003, or about 1/300, is shown in yellow. This is the median, or 50th percentile, meaning that half of the points are above the line and half the points are below the line. The most conservative attenuation factor returned by the Johnson-Ettinger model is at about this level, meaning that the model would underpredict risk for at least half of buildings. Finally, the 5th percentile of the database is at 0.0003, meaning that 95% of the data is above this line, and any proposed attenuation factors less than this number should be questioned. That plot was from data across the nation. How does California compare? For now, we're recommending to follow USEPA's national recommendation because it is the best documented and accepted database available. We will be building a California-specific database to see how California compares, and we may revise the recommendation in the future. I've covered the background. Now Dan Gallagher will continue this module with a summary of the guidance.